Hello dear audience, I'm Hamdouchi Chaimae, a PhD student in chemistry research and development, and I'm pleased to present you a part of my work about a sodium titanium phosphate as high-performance electrode material for sodium-ion batteries. As we all know, the very rapid development of onboard devices in electric vehicles, portable electronics, and also alternative energies, such as wind and solar power, has created a very high demand for lithium-ion batteries. The cost of these elements is constantly increasing, and its low availability around the planet creates great challenges. The use of another alkaline element such as sodium has therefore been considered for some years. Indeed, sodium is abundant, distributed all over the planet, inexpensive, and has a lower environmental impact. The working principle of sodium-ion batteries is similar to lithium-ion batteries, in which sodium ions get released from negative electrode during discharge, move towards positive electrode through electrolyte, where it recombines with just arrived electrons that have come through external circuits. On charge, this entire process is reversed. And recently, the development of new electrode materials for this new generation of batteries, especially polyionic compounds, has attracted the attention of researchers. The synthesis of our sodium titanium phosphate was done by the soldier route by mixing a stoichiometric amount of disodium hydrogen phosphate dihydrate dissolved in distilled water and titanium isopropoxide. After the addition of titanium isopropoxide, we have obtained a gel which was dried at 100 degrees for 5 hours and then annealed under air at 600 to 950 degrees for 6 and 10 hours, and by the end we have obtained a white powder. As we all know, the phosphate-based materials have poor electronic conductivity, so for that we proceeded to carbon coating process to enhance the electronic conductivity. Our composite material was prepared by mixing 85% of the resultant powder and 15% of sucrose using pure acetone as solvent. The mixture was calcined at 600 degrees for 5 hours under an argon flow, and by the end we have obtained the black powder of the composite material. Now let's move to the structural characterization of our material. The XRD analysis shows a pure and well-crystallized material which can be indexed into a monoclinic system with P2C space group and the following cell parameters. As we can see here, the structure of the sodium titanium phosphate consists in the arrangement of titanium oxygen octahedra sharing oxygen and linked 2 by 2 by phosphor oxygen tetrahedra to form chains, and the sodium ions are located between these chains. The morphologies of our uncoated and coated material were examined by scanning electron microscopy. As shown in the images of the uncoated material, the particles are agglomerated with an irregular shape and have a smooth surface, while from the images of the coated material we can see the fine carbon granules deposited on the surface. Raman spectroscopy was performed to investigate the carbon content in this coated sodium titanium phosphate. As the results shows, 2 additional broad and overlapping bands are observed, the D and G bands characteristics of carbon. And also, thermogravimetric analyses were investigated to estimate the carbon amount in the composite material. As we can see in the results, the amount of amorphous carbon is about 3%. Concerning the electrochemical tests, we have tested our material as a nano for sodium-ion batteries in a half electrochemical cell within the voltage window 0.01 volts until 3.0 volts in a current rate of 0.1 C. From the cyclic voltammetry tests, we can see a large primary cycle indicating the electrolyte's decomposition and the formation of a solid electrolyte interface layer. The 2 main anodic peaks observed at 1.55 volts and 1.42 volts are assigned to the oxidation process of titanium from 2+ to 3+ and then 4+, while the cathodic peaks observed at 1.3 volts and 1.1 volts are assigned to the reduction process of titanium. The following tests are galvanostatic and long-term cycling tests. As we can see in the figure of the galvanostatic test, our material exhibits an initial charge capacity of 160 mAh per gram at a current rate of 0.1 C. Also, one reversible plateau during the charge and discharge between 1.54 volts and 1.1 volt is observed, which is in good agreement with the CV results that we saw before. Also, our material shows an excellent cycling stability after 20 cycles and excellent capacity retention approaching 99%. After that, we tested our material by increasing the rate up to 1C during 50 cycles, and it maintained the high charge capacity about 112 mAh per gram, and excellent cycling stability and the capacity retention approaching 99%. More than that, the material exhibits an excellent rate capability performances, even if the current rate has been increased to its highest value. Moreover, when the current density returns to 0.1 C, our material recovers the same initial capacity of about 160 mAh per gram. To conclude this presentation, I will make the highlights on the main axes treated. A pure sodium titanium phosphate has been successfully synthesized via solder route. The carbon-coated sodium titanium phosphate presents an initial charge capacity of 160 mAh per gram with excellent cycling stability after 50 cycles and excellent capacity retention approaching 99%. As perspective, we are looking forward to perform in operando XRD analysis to investigate the structural evolution and the reaction mechanism during the charge-discharge process. We have reached the end of our presentation, and thank you, dear audience, for your attention.